Okay, we are going to keep to our timeline here, and I'd like to introduce G Gordon Worley III, who will be presenting on time series data in Postgres. Thank you.
All right, thanks. Yeah, I know some people are still out in the break, but hopefully we can entice them back in, right? With all these sweet details about storing time series data in Postgres. Yeah, so thanks for that introduction. Yeah, my name is Gordon, and I work at a company called AdStage. You'll see the little AdStage logo up there throughout the slides, you know. Can't help but use company template, right? All right, so a couple of things to get started with, just to give you a little bit of overview of what we're going to talk about today. First, we're going to go through some motivations. So what's the problem we're trying to solve? What were sort of the constraints? Just try to get a general understanding of what we're trying to do. Why am I trying to store time series data that I can update, right? Why do I even need that, and why do I want to store it in Postgres? Then we'll go through the experiments that I ran. So in order to come up with a solution, tried a bunch of different stuff, wasn't sure how to do it at first. I was convinced in my heart of hearts that I could make it work in Postgres, that I could get the performance I wanted. But I had to figure out exactly how to make that happen. And so I'll walk you through that process. And then at the end, we'll come back and look at some lessons learned. What out of all of that, even if, yeah, you're not going to go home necessarily and do exactly what I did, but what were some things that I learned that were takeaways that I think, can apply in a lot of situations? Okay, so let's start out by diving into those motivations by talking about the kind of data that we were trying to store. So if you've worked with time series data, you know that it sort of looks something like this, right? In ads, I work for a company called AdStage. We bring in people's ad data and then help them optimize it, analyze it, do stuff with it. So that means we're getting in all this data about ad units that are running out there in the wild, right? Whether those are like Google ads that you see on the side, Facebook newsfeed ads, display ads showing up on maybe a publisher website, right, like ESPN or something. All those things are generating data all the time, right? There's all these little events happening. People are seeing the ads, they're clicking on them, money is being spent. That data is being collected for each one of those little events, and then the ad networks provide that data to us aggregated up to some time slice, and that normal time slice is a day. So we get back data that looks like this for each ad unit, right? It's got a date, and then I've got some metrics associated with the ad for that date. Okay, so far, great, right? That seems like normal time series data. I'm getting one of these data points every day. This seems like pretty low volume. Shouldn't be a problem, right? We should have tons of choices about how to store this data. Except this data is mutable because of ad fraud. So in advertising, this aggregate data, the events that happen, just because the event happened, just because someone clicked on your ad, just because someone saw your ad, doesn't mean that that counts. And the reason for that is that on the publisher side, there's a lot of fraud. There's attempts to essentially game the system, generate revenue for the publisher of the ad by generating what we would call like fake inventory, right? These are ad units that get displayed, get clicked on, but no human was ever involved. There was some bot running. The ad networks are pretty aggressive about trying to deal with this problem, and they have a bunch of machine learning solves this problem. What happens for us, though, is that means that up to, say, like 30 days after the event happened, right after the day, that data might be revised because their algorithm goes back and identifies that, oh, this click was fraudulent or whatever. So that means these numbers are going to get updated. And given that's the case, that knocks out a lot of potential ways that you might try to store time series data because it's going to be modified. Now, I'm talking to you today about how we store it in Postgres, but for a long time we didn't do it this way. Previously, and for about 5 years, we stored it in Cassandra. Our reasons for choosing Cassandra were somewhat vague, right? We were excited about it. It was going to deliver web scale, right? That sounded great. So we were pretty gung ho on Cassandra. I'm not too proud to admit that I did some stupid things in Cassandra, like I eventually just had to rewrite essentially my own relational database inside Cassandra at the application layer. Not a good choice, but you can do it. Cassandra, for this particular problem, though, had some specific issues, right? So we were storing this time series data in Cassandra. Parts of it were working, but parts of it weren't. One problem was it was expensive. I won't go into all the details about it, but because of the way the data is structured and because of operational constraints around how you need to run your Cassandra cluster and have it be reliable, that meant that our cluster was more expensive than we would have liked it to be. Also requires a lot of application logic. If you've not worked with Cassandra, a good way to explain Cassandra is that it's not a database, it is a data store. It's very good at storing your data. It's very good at retrieving your data. It's not really very good at doing anything else. So if, for example, if you want indexes, why would you want that? I don't know. But if you want them, you basically need to roll your own if you want them to function well. Cassandra does have built-in indexes. Don't use them. They're awful. It also doesn't really provide aggregation or joins. So if you want to do those type of operations, your only real option is to pull the data out and then do those operations in your application logic, right? So you're reinventing the wheel a lot to use Cassandra, and that's what we had done. It's also hard to change. So if you want to make major schema changes, you're essentially left in the situation of extract all the data from the database and put it back in. That's not great when you have terabytes of data. So when we were thinking about the desiderata for our new solution, we knew that we wanted to make some improvements over the old system in Cassandra, but we also needed to maintain some of the stuff that worked about it. So that included supporting a high write volume. We averaged greater than 10,000 writes per second for all this data going in. And when I say 10,000 writes per second, that's like, each write is essentially like 1 day's worth of data. We spiked to well over like 30 or 40,000 per second, sometimes of the day. So we needed to be able to support that load. Needed reasonable write latency. We really care about throughput. Because of the way the data pulls in from the APIs, we actually have a few hours of slack. So, okay, latency doesn't need to be in the microseconds. That's not necessary. But the latency has to support the write throughput that we need. We have comparatively low read volume. We probably do hundreds of reads per second. So, the needs there are a little bit different, right? We also only need to support relatively moderate read latency on these queries. We'll talk a little bit more about the type of queries we do in a minute, but something like 2 to 5 seconds is pretty adequate, right? Our customers, we're delivering a lot of queries that are doing complex BI type analysis, right? Their alternatives are, maybe you do it in a spreadsheet where it takes minutes maybe to do this calculation, or you have to build something custom. So they're fairly happy to wait a few seconds to get a response. So we don't need those like super short times, but no one wants to wait a minute to get their data back, right? And then last little catch here, just to make things extra complicated, right? The list of metrics we store. So you saw back here, I had like impressions, clicks, conversions, spend. These are just 4 common metrics, but in fact, there are literally thousands of metrics that we store in our system, right? I want to say that the current count is somewhere around 5,000 or 6,000. And they're all different for different customers, for different ad unit types. Some customers have custom metrics. For example, if you ever do any Facebook advertising, you can create these like custom Facebook conversion metrics. That means you have a time series identifier now for your data that is unique to just you in this one advertising account. So we needed a great deal of flexibility around that. Okay, so all those things were being delivered by Cassandra. We also needed to deliver on some additional things. We wanted it to be more cost effective. We wanted to get out of the business of having to do our own work with aggregations, right? We wanted something that supported time series and aggregate queries on our data. And then, of course, we wanted flexible schemas. In our business, things change a lot. There's always new ad networks coming in. They've always got different things. We're trying to deliver, new features to our customers. We didn't want schema changes to get in the way of delivering that, right? Because they had actually in the past, right? With Cassandra, it sometimes would slow us down of just, okay, it's going to take months to do this because we'd have to read all the data out, write it back in. Is there something else we can do? It was putting a lot of constraints on us. So given all that, I said, okay, let's try, or not let's try, but let's think about a few different things that we might try, right? So this is a short list of some of the things we evaluated. Obviously, I've already knocked off all the stuff that, there are time series databases that can't handle very well data that gets updated, like they just don't support it at all. So those things have already been filtered out here, basically. So we have a few options and started looking at them, and he said, well, some of these things don't really work because they're not going to support the broad range of queries that we want, right? They're sort of designed around either specifically supporting time series data, or they have, like, they're fairly restricted in other ways. They weren't going to give us broad ability to just perform ad hoc queries that would do whatever we wanted. We also wanted operational simplicity. So I knocked off one thing here, which is Druid. If you've not looked at Druid, it's super cool. It can get pretty good performance on lots of like fine-grained event data and let you do complex analytics queries on them with pretty good performance. Unfortunately, its deployment story is extremely complicated. It's got multiple parts. It requires other parts to supervise those parts. And at least at AdStage, we're a fairly lean startup. To give you an idea, my job is both head of SRE, I don't know, DBA, right, lead engineer, a bunch of stuff, right? I don't have time to work with something that's, you know, got a lot of operational complexity. And then finally, I'm just going to knock off these other two, mostly because they suck. But in the slides, I was nice, and I said ease of use, right? But if you've worked with these things, you know they have problems, right? Both Elasticsearch and MongoDB could theoretically work here. However, they also lose your data, so that seems like a problem. So of course, in the end, you know, said, okay, relational database management system, I think we can do this. And of course, the answer was Postgres, right? Why Postgres? I don't think I have to convince you all too much, but you know, I think it's pretty battle tested. Lots of people have used it for a long time. I've used it for a long time. I like it a lot. It's extremely flexible. You can basically make Postgres do whatever you want. It can be whatever kind of database you want it to be. It's widely adopted, very nice. You search stuff up, you just find an answer, right? Some databases, you search for things and you're maybe the first person that's ever run into this problem, and that is all very rarely the case in Postgres, right? Usually the problem is I find 4 or 5 answers, and I have to try them until I find the one that works. Extensive tooling and integrations, that's great. And of course, we can make Postgres work with our use case. If you remember, you know, we talked about read and write volume. I will tell you that we experimented with using RDS for our use case. I don't know if there's anyone from Amazon here. RDS is a very nice product. I use it for like application databases, but for storing this data, it wasn't performant enough. Essentially, the limitation is EBS. However, Postgres, you know, it'll work great. If I throw a high-performance disk at it, it can use it. And in our case, you know, Postgres is very happy to let you shard it right at the application layer. In this talk, I won't really talk about how that all works in our deployment, but it's actually pretty interesting, and maybe I'll give a talk on it at some point. But regardless, our data is federated. You know, it's separated by customer, and that logical separation makes it very easy to have physical separation. We never do queries that like join across customer accounts. So that made that pretty easy. So all that out of the way, we've decided on Postgres. Great. Now it's time to start running some experiments to figure out how the heck do we actually store this data and make it work. So to give you the setup, tell you about some of the conditions for these experiments. I want to tell you about our average worst case customer. So maybe not every customer is literally this bad, but this is something like 98th, 99th percentile customer, right? They have, we're going to call it 10 million ad units. That's maybe not literally ads, but you can just think of them as ads. They have approximately 3 months of data. So here, to round things off, I'm going to call that 100 days instead of 90 or 91 days. That's not always true of every ad unit, right? Some of them run longer. Some of them are what are called like evergreen campaigns, ad campaigns, and they will run for years. Others are very short-lived. They might run for a day, a week, and they're gone. 3 months sort of just rounds it out to about what is normal, right, which is a quarter. Obviously, we could have gotten a little more complex here, but we felt that for testing, this was good enough. Gave us a good enough approximate. And then we're going to say approximately 100 metrics, right? Very few of our customers store for any individual ad unit more than 100 metrics. An individual customer might have more. We have individual customers with as many as, say, like 2,000 different unique metrics. But, or, you know, if you to use other, we call them metrics, right? They're sets of time series data with a unique identifier. So there's about 100 of those per ad unit. And then the test query that we're going to run wanted to come up with what was sort of our what's like an approximate of the most complex type of query that we run. And what we came up with is, okay, we're going to do an aggregate operation on the individual metrics time series, right? Then we're going to do this across some subset of the ad entities. Typically, in a query, you're pulling out some chunk of ad units that have some property that's been filtered some way. So we're going to simulate that by pulling out some subset of them. We said 1,000. That's pretty normal for a query for us. And then it's going to be grouped by week. I chose to do grouping by week simply because it's simple. It would also expose any, because it's not cut along a nice, easy date chunk, it prevented me from cheating, right? I couldn't cheat and be like, oh, let me try partitioning the data a special way or something like that. I would have to deal with the complexity of aggregating across arbitrary time ranges. But it's also a stand-in. We sometimes aggregate. It's a BI system, right? Sometimes we aggregate by things that are not time, right? Data gets joined against other tables, and maybe you're aggregating by targeting criteria for an ad or whatever. And then finally, the hardware we're going to test this on, we run it on AWS, run it on i3 Metal. This is also what I run in production. The i3 Metal, if you've not used the i3 series on AWS, it's essentially a high-performance storage option with high-performance SSDs. There's, you know, various classes of instances you can get on AWS. This is probably the best in terms of if you just want like high, excuse me, the other way. If you want very low read and write latency, this is probably the type of instance to get. And then we're doing it using PG11. I'll show you a few numbers, and that's what those come from. Now, I've just lied to you about some of this, though, because when I actually ran the experiments, I didn't know what I was doing for some of it. So I ran them a little bit over like a year and a half ago, I guess. So at the time, obviously, I used Postgres 10. Postgres 11 was maybe just about to come out. I don't remember. Yeah, so there's that difference. It didn't substantially really change the numbers, but you know, it's there. Some of the initial experiments were also smaller, so I'm going to tell a very nice story about the experiments, but in fact, when I started the experiments, sometimes I didn't know like what my average worst use case was. It took me a little bit to understand my data very well and what I was really targeting. So I sometimes spent more time than I'm happy to admit trying out solutions that in hindsight were infeasible, could never have worked. I'm also only going to talk about our time series tables. There's other parts of the system. I was testing them at the same time. We join against all this. We have all this what we call metadata about the ads. That's like targeting information, bidding information, yeah, just all kinds of stuff that our customers care about, but we're not going to look at it here. We want to keep it simple. And we're also just going to ignore indexes for the remainder of this talk. I definitely use indexes. You won't see any discussion of indexes. Index appropriately, but they don't really make a difference to the story, so we're going to leave them out. But feel free to ask questions about them later if you have some. Okay, so given everything that I've done to set us up, I started with this sort of naive approach, right? I said, okay, let me try to do it by the book maybe a little bit, right? I have these time series, like these individual values, right, that are uniquely identified by an add unit, which I've here called entities. So you see that in my table, right? I have this entity column. It's got an identifier by a date. Here I've called it TS for timestamp, right? I've got that column. I've got metric, so I've got the name of the metric. So those three things uniquely identify each value in our time series. Okay, what if I just did something like this? This gives me a ton of flexibility, right? I have a lot of options in how I can write my queries. I can do everything in SQL. I don't need a lot of application logic. What's the story here? Well, unfortunately, this doesn't really work that well, right? If you remember our average worst use case, let's say that like all of customers' data is in their one table. You multiply things out. Well, now you're looking at 100 billion rows in this one table for this one customer. I don't know if you've ever worked with a Postgres table with 100 billion rows. It's not the best experience, right? It can work. I'm not going to say it can't. However, depending on, especially given our write volume, and then what that meant in terms of making replication work, what that meant in terms of making auto vacuum work to prevent transaction wraparound, it just meant that this was essentially unworkable. Okay, so that's way too big. I said, all right, well, how can I improve on this, right? What if I just denormalized a little bit? And I pivoted those metrics up into rows, into columns, right? So instead of having one row for every chunk, or for every value, let me just store all the 100 metrics that are associated with a particular entity at a particular time in a single row. It seems like a reasonable improvement, I think. It's going to cut down on our table size. But, there we go. Really still too big, right? Like, okay, I cut down our 100 billion row table to a billion row table. That's still kind of too big. But I thought, maybe if I keep pushing at this, right, I can make it work. So what I call attempt 2.5, I just said, okay, why don't I partition, right? Let's try partitioning. Now, the real story is that I tried partitioning all kinds of different ways. I'm going to show you one way to partition it. Honestly, none of them worked. This is just a stand-in for the fact that none of my attempts worked. So if we try, say, one-day partitions on the date, now we're down to just 10 million rows per partition. That's workable, okay? I can tell you that, in fact, in our production systems, I am pretty happy with any table that is 10 million rows or less. If anything gets over 100 million, I know I'm going to have problems, right? My replication falls behind. I can't really run vacuum fast enough to both serve queries and prevent transaction ID wraparound. So, 10 is great. It's an order of magnitude less than my limit. Seems reasonable. How does this perform? Not great. If I write a sample query, and here I've sort of got an elided version of a real query. The real thing just takes up a bunch of space, doesn't really tell an interesting story. So here I've got sort of a hand-wavy version of the query I ran. You can get the idea of it, though. I'm selecting out some data from the table, putting some constraints on it, and then aggregating by the week. Even with the partitions, this thing takes like 300 seconds to complete. Okay, well, that's a start, right? Now we have something that returns something. That's better than nothing. And then I thought, you know what? Probably somewhere around this time, I saw a blog post about this thing, which is timescale DB, right? They're here. I thought, okay, why don't I try timescale? Whoops. There it goes. And it's substantially similar, in some ways to the solution I just proposed, right? I'm going to let timescale handle the partitions. But that's essentially what's happening is I pass in the table, I tell it, hey, here's the column with the time in it. Go ahead and do your thing, right? Figure out how to partition this data, manage it for me. You do it for me. There's some nice things about timescale, right? I don't, as you'll see in the next slide, I don't really have to change my query any to work with it. It just takes care of things for me in the background. That's nice. Also, the documentation says, seems like it should support it, right? What do they say here? 10 plus billion rows, sustained insert rates of 1 to 200K. Great, that sounds like it should work for me. Let's give it a shot. Unfortunately, my experience with timescale was that I got essentially the same performance as partitioning. Now, to be fair to timescale, I'm not quite using it the way it's supposed to be, right? I'm updating data. So that's going to reduce my performance. There's probably some other limitations. There are likely additional things that could be done with my data that may have made it perform better in timescale. But after playing with it for a while, I just couldn't figure out a way to make timescale DB work for me, right? And also, in fairness to timescale, this was in the past, so timescale may work different now. I don't want to say anything disparaging about timescale, especially since they're here, but that was sort of what the situation was for me. So this meant, okay, I got to step back and say, what's going on here, right? What is the problem with these solutions? Why are they not working? And thankfully, we've just had a great talk on Explain, which is going to come in handy, because, yeah, what I need to do is really analyze what was going on in the explains for the queries and try to understand what were the limitations of these queries, and maybe that could point me towards a solution. So the main thing I discovered in the explain was essentially I had too many rows. There's two ways to explain this, right? One is that I was running out of memory. So even when I would bump up work mem, sometimes it still wasn't enough, right? I was having to give, in some cases, my workers like 2 gigs of work mem in order to not ever go out to disk to perform operations. That's a lot, right? I've got a fairly limited amount of memory on my machine, even if it is an i3 metal. I would still like to run more than, 20 workers on it, right? Also, if I was going to use that much memory and support that few connections, I might as well just use like an analytics database, right? Like something that is like, there are, for example, like forks of Postgres that are designed specifically to support analytics workloads. Maybe I could just go that direction. I've used them before. I sort of understood their limitations and why they wouldn't necessarily work for us. But if that was going to be the case, I might as well just do that, right? And stop trying to reinvent the wheel. I was also hitting lots of disk pages. So this is what really got me thinking, is I noticed that in the explain, what's happening is that ultimately I am pulling a ton of pages from disk. Like even if I throw a bunch of memory have a bunch of memory for the worker, it doesn't have to write out the disk to do its, like during a hash aggregate step or a merge join, it doesn't have to do anything out to disk. I was still losing a ton of time just reading data off the disk. That was absolutely the biggest chunk of it, right? Like of that 300 seconds, maybe 250 of those seconds were just reading data off of disk. And keep in mind, this is with high performance SSDs. So I said, okay, well, how can I just get less data, right? Like, I guess I can't get less data, but how can I get fewer rows? So there are a lot of options here to reduce my amount of rows. I started thinking about ideas. What if I use like some sort of columnar storage, right? There are extensions for Postgres that support columnar storage using the foreign data wrapper interface. Maybe that's an idea. Maybe there's like, I could use JSON, right? JSON-B, we talked about that earlier. Maybe I could use XML, because I hate myself. Maybe I could just store raw bytes. I could store raw bytes in there and write a bunch of C functions to process it. I wasn't quite sure where this was going to lead, but I said, okay, let's start experimenting with this. What can I do that can get me fewer rows? And I thought, well, what is columnar storage really, right? Columnar storage is not too much other than an array somewhere else. So I said, aha, I got an idea. What if I just had all my arrays toasted? Wouldn't that pretty much be columnar storage? So that was my idea. So to step back and explain a little bit about what's going on here, I've changed my schema a little bit, right? So now I've taken out the date column, and we just have the columns for the add identifier, so the entity column, and a column for each metric. And each one of those columns is now an array type. You'll notice it's a numeric. This is because sometimes the data that we get is money, right? It's money, it's information about spend or something like the amount of money that was spent on an ad. If you've ever tried to store money in a float, don't, right? It's bad. There's weird rounding errors, and those matter for us. Believe me, I've worked in ad tech for a while, and to me, despite the fact that the margin of error is like fairly high, because if you work inside an ad system long enough, you get to understand that there's like a 1 to 2 to 3% like fudge factor on a lot of this information, right? Like you can't really get accurate performance data. There's just too much noise. But advertisers are very aware of exactly how much, like what it says in one particular system. And if it doesn't exactly match in all cases some other system, they're unhappy. So you've got to be able to do precise calculations, even if it doesn't really matter. So given that, now tell you a little bit about what's happening here. We're using the arrays. The way that we're using the arrays is essentially that the index into the array is a date. So you set an epoch, right? You say like, okay, my epoch is going to be, here in my example, I say it's 2020-0101, right? January 1st of this year. Then the array position is essentially an offset from that date. So date 0 is going to be that date. Date 31 is February 1st. If you go back in time for some reason, the negative 31, that will be that point in time. And if you've not worked, we talked a little bit about, you saw in the earlier talk a little bit about Postgres arrays. One of the really great things about them is that they're sparse, which just means that when you store data in a Postgres array, it only stores the data for the range that you care about. So when I set that epoch, like in my production system, it's set at January 1st of 2001. That's well in the past of any data that I have, makes it super safe. It doesn't have any performance impacts, though, because when I start storing the data, it just keeps track of like, oh yeah, the first bit of data you stored, this is the index associated with it, and it just stores that data. It doesn't fill in a bunch of nulls or anything like that, at least in terms of when it stores it. Now, the other trick to this is that our data often ends up big enough to be toasted. So if you've not worked with the toast system, just to tell you very quick answer on what is toast. It's a subsystem in Postgres that deals with large data. So if you put data that is bigger than the size of a page, for example, and in Postgres by default it is compiled such that a page is 8K. If your row exceeds 8K, I don't know, it can't store it. So to store data bigger than that, it has to use this system called toast. Toast stands for something cute. Toast is like a cute acronym. I forget what it stands for. But the way it basically works is you put it in. Now what gets stored in your row is a pointer. And it goes and it looks up out in the toast table the value that you wanted, right? And the toast subsystem is able to store data larger than a single page. So this is really neat because if you remember, one of the problems we were having is we had too many rows. So the nice part about this is that not only can I get fewer rows, I can actually just get less data overall, right? I can also use less memory because in any one of my queries, I kind of, I think, skipped over this detail a little bit earlier, but I'm usually only pulling back a few metrics at a time. It's rare that I want every metric at once. So that means that I can actually get a lot of benefits and save a lot of resources if I don't have to have all that data in memory all the time. So by moving it, having it shoved out somewhere else, I'm not constantly loading into memory, having it slow me down. So I made this modification. What happened? Well, works pretty well. Got my queries down to about 60 seconds. That's pretty good. This is still, though, true only if I gave them a lot of memory. And you can see here sort of what the query looks like. And you'll see the introduction of this new operator, which is called a nest. So if you work with arrays, you have to sometimes unnest them. What unnest does is essentially turn your array into a record set. You can join them up with other arrays. In fact, if you select out unnests like this, it will very nicely zip them up, as we say. It'll make them line up, and you'll get back a record set that looks very nice. It's great. However, I said, okay, this is kind of complicated, and I looked at the explain, and what I learned is that unnest was actually my new bottleneck, right? So unnest, even if it weren't a bottleneck, it has some just query complexity issues. It's fairly complicated to work with, at least in my opinion. I've written some queries with unnest, and it was very confusing to me what my query was even doing. It required a lot of complicated logic to handle the slicing of sparse arrays. This basically had to do with boundary conditions and the fact that I would sometimes have nulls in one place, nulls in another place, maybe a gap in the middle. Getting everything to line up was a little bit complicated. Also required a lot of coalescing of nulls. If you've ever worked with, you've probably seen this, you go to do an aggregate, right? If you ever do an aggregate function and for some reason you unexpectedly get back a null, it's probably because one of your values was null somewhere. This was happening a lot, so it meant that we had to deal with coalesce statements everywhere. It was just, again, adding to query complexity. Required a lot of memory usage because once you unnest all those things, now you're essentially back in the situation of we originally were in, where we just have all of these rows, right? Yeah, they're not on disk, but they're still in memory. So it was still eating up a ton of memory, and that meant that when I went to do things like grouping, joining, it was slow. So I said, okay, well, what if I just didn't have to unnest? And I thought about it, and I realized, you know what? I'm just working with arrays. Why do I need anything more than a for loop, right? Why am I trying to do this all in SQL? Can't I just, iterate over the thing and get what I want? It should be pretty simple. So that's sort of what I did. I said, you know what? Let's replace unnest with just some functions, and we'll make sure those functions are able to execute efficiently. And that's what we did here. I'm running a little short on time, so I won't go super into detail on this. Other than, to make this work, you need to execute your functions or set some flags on your functions that make sure that they execute efficiently. For us here, because we're doing just numerical calculations, we're not accessing anything in the database. It means that we can take advantage of a lot of modern features of Postgres, like its ability to run things in parallel. You just have to set up your function appropriately so that it will use that system, in addition to having your Postgres comp set up to work with parallelism. So you do that, you're going to get a lot of performance benefits, and the result was I could take this thing, and in my worst case, I could get my result back in about 15 seconds. And you'll also see that the query gets a lot simpler, right? Because I shoved all the work into this function. But this function is not super complicated. It's just doing very straightforward procedural logic on the array. Now, that 15 seconds is really a very worst case scenario. The reality is that the P98 in production is 3 seconds or less. Sometimes it inches as high as 3 seconds if there's a bunch of secondary stuff going on in the database. But yeah, it works really well, and it serves our customers pretty well. So that was really the trick, was getting it to that point. Okay, so that was, just very specifically, though, for us, how we did it and what worked for our particular use case. What are maybe some lessons you can take away from this? I think the big one is maybe fewer rows or better performance. This is sort of obvious in hindsight, right? Duh. If I have less data, everything is faster. But what this means more practically is that I think sometimes we have to think about it in schema design, right? I started out with a very normalized schema. I denormalized more and more over time. I think this is a common story. you have to make a trade-off, right, between how normalized do you make it, how easy do you make it to query the data, versus how much do you denormalize the data, couple it with application logic, but improve performance as a consequence. So that was, an important trade-off to consider here, and I think, makes a big difference for whatever you're doing. Arrays plus toast is approximately columnar storage. I was surprised by that, but this is basically, as far as I'm concerned, the 80-20 on getting columnar storage in Postgres. If you're doing have append-only data, you can definitely do better, and you might have performance requirements that require better, but this is very easy to work with, doesn't require any extensions, so worth taking into account. And then finally, that functions can often perform better than SQL for array operations. So if you're working with arrays, consider using functions in order to speed things up rather than trying to do all your work in just SQL and using things like unnest. Okay, well, that's sort of all the slides I have. So now we've got a little bit of time. I know I ran over a little bit, but I think we got some time for questions. Yeah? Whatever you want is fine. Yeah.
You mentioned earlier that when you tried out RDS, you didn't like it because EBS was a performance bottleneck.
Yeah.
So I take that as a suggestion that when you set up i3 Metal, you actually use instance disks.
Yes.
Doesn't that mean you have a now replication problem to solve?
Ah, okay.
Like persistence in general?
Yes. Yeah, so the question is, since I am using an i3 Metal and not RDS, I'm using instance storage, and so the question is, doesn't that mean I have to deal with data reliability, essentially, right? And the answer is yes, right? So this is one of the very nice things that RDS gives you. Because it uses EBS, it's able to, if you're not familiar with these acronyms, sorry, EBS is Elastic Block Storage. It's Amazon's persistent network area storage. It uses it to back all RDS instances. There is no support for instance storage as far as I'm aware on RDS. This means that backup replication, it's all like very straightforward, and you have this nice backup of the data is persistent somewhere, right? If you're using instance storage on Amazon, there is no persistence, right? So that storage is attached to the instance when you allocate it, and when that instance is gone, your storage is gone. You lose those disks, you don't have them anymore. So yes, what that means is that, yeah, I have to have backup, I have to have, in my case, yeah, I do replication, right? We run warm standbys. We're able to fail over immediately if anything goes wrong. But yes, it does mean having to handle that, and that is one thing that you give up by not getting RDS. All right. Yeah. Yes.
Did you try Aurora?
I'm sorry.
Did you try to test with Aurora?
I didn't quite catch the last part. Did I try the
Aurora.
Oh, Aurora. Oh, yes. Actually, I have nothing but bad things to say about Aurora, so I will not say them. It's possible that it's because I was a beta user for Postgres Aurora. I ran into nothing but data faults, right? Like basically Postgres Aurora lost my data repeatedly under load. Maybe it's better now, but that was my experience of it, right? So, but I will tell you that I was a pre-release user of Aurora for Postgres, so maybe that's all been solved now. I can only speak to like what my own experience of it was.
So every time you add a value to an array, you need to rewrite the whole array, right? So how
Yes.
is your write performance looking?
Oh, how do I do the, okay, so yes, so, right, I'm storing all the data in an array, and he's asking about how I do the writes. So yeah, there's two things to note here, right? And this is based on my understanding of Postgres. I may be wrong about how the internals of this work when I say this, so if that's the case, please correct me. So one part is to do the writes. It's fairly nice when you write into a Postgres array. Because they're sparse, you can essentially just update the indexes you care about. So it generally just works this way. You say like, okay, I'm just going to write like this 5 days of data. I just specify those 5 indexes, maybe as a range. I say here are the values. Boom, they go in. It gets updated. from the description layer, it's very nice, right? Like I just write super simple. However, in terms of how it gets stored, my understanding is that every time I do the write, it's rewriting the entire thing. So that entire array does get rewritten. It turns out that for practical purposes, this isn't much of a problem. However, that mostly maybe because I'm using, the i3 Metal has 8, I forget if they're 2 terabyte disks, right? So it has 8 2 terabyte high performance SSDs in a RAID array. And also, I don't own them, right? So I don't care that I've like exhausted these SSD drives, right? So I just abuse them, and it works out great. And then if the thing has problems, I just throw it away and spin up a new one. So yeah, that is like a caveat to this, right? And depending on what your situation looks like, that may or may not be a choice that you want to make. But in practice, it turns out that like most people don't look like our worst case. They're much smaller, and so it's not actually a problem in terms of like write performance. Say to like be continually writing a large amount of data like that.
How many writes per second you make?
Yeah, typically the system, I peak it out around like, for an individual shard, I like to keep an individual shard under 8K, 8,000 transactions per second, which is primarily all write transactions. If it goes much above 12, I start to see problems with replication delay. I haven't entirely solved that, but it seems to be not a network bottleneck. It just seems to be a Postgres bottleneck. It can't seem to process the wall, like on the slave, fast enough to keep up. So I'm not sure what the issue is there. I've tried lots of stuff. And certainly by the time I get to, but theoretically the system can support 20, 30, 40,000 per second and keep up with it and still perform. It just falls behind on replication. So that's the only real difficulty there. Yeah.
So my question, just because this is my whole life, unfortunately.
Yeah.
When you evaluated RDS, did you try the different disk types?
Oh, yeah. So the only thing I did not try was provisioned IOPS.
That would have bought you a lot, because I work at Heroku, and that's what we have
Oh.
all the time is people on our lower tier plans, we use provision IOPS, we use burstable ones, they
Yeah.
complain about performance, things are terrible, we go to a PRIOPS plan,
Yeah.
and suddenly it's like, it's perfect.
Yeah, so I'll tell you that maybe Amazon is lying in their documentation. It's possible. The deal with provisioned IOPS seems to be that provisioned IOPS, as far as I can tell, now we're on like a side issue, but it's related, is a bad deal, right? So the specs say that if you have, because you can now allocate up to like a 16 terabyte drive, right? The cost to allocate 16 terabytes of EBS and the amount of promised IOPS that you get for 16 terabytes is cheaper than what it would cost to get you the same amount of provisioned IOPS on a smaller disk. So it appears that if you just ask for 16 terabytes, you get the maximum possible amount of performance on EBS, which is what I did, and it still wouldn't perform well enough. That's all I can tell you, right? I was somewhat unwilling to like pay for provisioned IOPS given what the documentation said. But yeah, it's possible the provisioned IOPS secretly work in some way that is contrary to what the documentation claims. All right, anything else? I feel like we must be out of time, but we got one more.
Sorry, so I just wanted to ask if you tried
Yeah.
to quantify when you were looking at these explain plans, how much of your time was spent like toasting and detoasting things versus the rest of the query time?
No, not really. Excuse me. Basically, when I got down to the point of heavily relying on Toast and being in a position where I knew I was using Toast because, I can see the artifacts of it in the database, right? I can see, if nothing else, my row is just impossibly too long, right, to fit. Then, yeah, I basically got adequate performance for my needs, and I didn't bother to investigate further. But yeah, it's possible that, yeah, there is more potential to learn in there. Okay, oh, there's one more. Yeah.
Since you already told us that your customer data is already federated by tenants,
Yeah.
why do you really need to, because the data was, whatever you're looking for is separate for every tenant, right? So why do you need to store all the tenants data in one cluster?
Oh, okay, right. So since my data is federated, why do you need to store it all in one cluster? Essentially for operational ease, right? As I said earlier, I am it, right, for dedicated operations staff, and it's not even my full-time job. So if I had to deal with, say, one database per customer, which would be a very traditional, like, sort of federated approach, right, of having physical isolation for every customer, yeah, maybe that could work, but that would add a lot of operational complexity on our side, right?
I mean, instead of choosing your own IP instances for every 1,000 customers, there's a group of tenants you can go with RDS, which has capable enough of your IAP and storage and memory, and they manage your operations part, right? Like scalability.
Oh, yeah.
All this stuff.
So yeah, you're right that, yeah, the comment here is that, oh, well, doesn't, RDS manages a lot of this, so like, doesn't that simplify the operational story? And I think the answer there is still that, essentially I would be looking at dealing with hundreds, maybe thousands of RDS instances to support this. And, if I wanted to say do like one per customer, that just wasn't really the route I wanted to go. I honestly don't even know the scaling limits if Amazon will let me do that or not. So yeah, that seems like a limitation. I'm getting the sign here though that we're at 0. So if you have further questions or want to discuss things, let me know. But yeah, I think that's it.